Let's go, everyone. Imagine a cataclysm that destroys all scientific knowledge. What would be the one sentence that could convey the most information to future generations? That sentence is, everything is made of atoms. Simple, yet powerful, isn't it? Now, picture this. A spaceship preparing for an epic adventure. The nervous crew is about to explore a natural satellite, but it's not just any satellite like the moon that Armstrong and Aldrin visited. When those astronauts traveled, they had to cover the distance of 30 Earths. Our adventurers have to cover a distance 63,000 times greater than the diameter of their planet. Their satellite moves at more than 2 million meters per second, almost 1% of the speed of light. While the moon seems like a celestial snail compared to this satellite completes 6.5 quadrillion orbits per second. But wait, the adventure is not in outer space, but in the atomic realm. Our intrepid travelers are inside a hydrogen atom. Leaving the lone proton at the center, they seek the single electron that orbits it. But their mission is much more difficult than it seems. Modern quantum physics tells us that we can never know exactly where the electron is. We can only say where it is most likely to be. So our travelers could never land on the destination, only float in the fog of possibilities. Atoms are like the Lego blocks of the universe. Vast galaxies spin in the void. Distant stars watch over the night, but everything is made of atoms, including us. The number of atoms in your body is greater than the total number of stars in the observable universe. And within these atoms, there are complex systems waiting to be explored. A furious wind howls across the Black Sea. The waves churn and break as the water, once calm as a mirror, transforms into a whirlpool. Lost in a kayak in this chaos are two newlyweds. They are refugees, fleeing Ukraine to escape the Russian regime. But this is not a story from the 21st century. The year is 1932, and the couple trapped in this storm is physicist George Gamow and his wife Lyubov, whom he affectionately calls Rho, in reference to the Greek letter. But what could lead this young couple to risk their lives on such a dangerous journey? In the 1930s, there was a significant change in how the Soviets treated their scientists and intellectuals, and foreign travel was increasingly monitored. Gamow wanted to present his research at a major scientific conference in Rome, but he needed a new passport. His application was constantly delayed by bureaucrats in Leningrad, who promised progress but were actually just buying time. He never made it to the Italian capital. However, his endless visits to the passport office had a significant positive outcome. It was there that he met Rho. They married shortly afterward, and in less than a year, decided to flee. They analyzed maps looking for the safest route to escape the Soviet Union, and so they decided to cross the Black Sea, leaving Odessa, Gamow's hometown, heading for Turkey. Gamow still had a Danish motorcycle license from his time collaborating with physicist Niels Bohr in Copenhagen, and the plan was to reach a Turkish beach, pretend to be Danes, and ask to be taken to the Danish embassy in Istanbul. They secured passage to a scientific conference in Belgium, and after the conference, Marie Curie helped the couple extend their stay in Western Europe. They never returned to the Soviet Union, and in early 1934, finally left for the United States. This entire odyssey happened before Gamow's 30th birthday. 6 years later, Gamow was granted American citizenship. Free from the shackles of oppression, he was able to continue his work. And it was this work that would prove fundamental to our understanding of physics, as it would forever change the way we think about the history of the universe. In 1929, 3 years before Gamow's adventures in the Black Sea, American astronomer Edwin Hubble shocked the scientific community with evidence that the universe is expanding. If the universe is growing day by day, then it was smaller yesterday and even smaller a week ago. Going back in time, there was a moment when the entire modern universe was concentrated in an incredibly small space before expanding. The Big Bang. But this was not a new idea for Gamow. Russian physicist Alexander Friedmann had already predicted the expansion of the universe in 1925, and the two had long discussions about it during Gamov's time in Leningrad. Gamov spent much of his early years in America working on something else, the energy source of stars. However, the focus of his attention was changing. In October 1945, Gamov wrote a letter to his old friend Niels Bohr to celebrate the Danish scientist's 60th birthday. The letter reveals that Gamow was beginning to apply his work on the internal mechanics of stars to the origin of matter in the early universe right after the Big Bang. Up until then, cosmologists assumed that the early universe was dominated by matter, the substance that forms all visible structures, from stars and planets to galaxies and galaxy clusters. However, Gamow began to suspect otherwise. The story varies about who really deserves the credit, but it may have been Gamow's student, Ralph Alpher. In his doctoral dissertation, Alpher claimed that the early universe was not dominated by matter, but by electromagnetic radiation. This electromagnetic radiation supposedly dominated the early universe for about 50,000 years after the Big Bang. Physicists have another word for electromagnetic radiation: light. We use this word for the light our eyes can see, but there's more to it than that. Just as there are sound frequencies too low or high for our ears to hear, there are light frequencies too low or high for us to see. When a physicist uses the word light, they refer to radiation that spans this entire range of frequencies, from gamma rays and X-rays at the high frequency end to microwaves and radio waves at the other end. When you use a microwave to heat your dinner, you are actually cooking the food using low-frequency light. And so, light and matter were trapped together in the nascent universe. After 100,000 seconds of expansion, the entire universe was still denser than the air you are breathing now, and it continued to be dense enough for sound waves to travel through it for thousands of years. Sound waves of such low frequency that they would need to be compressed by 100 septillion times. That's 1 followed by 26 zeros, just to push them into the human hearing range, something that, in 2013, John G. Kramer from the University of Washington used early universe data to reproduce. Cosmologists call these sound waves baryon acoustic oscillations. As the universe continued to expand, it kept stretching these sound waves, shifting them to lower and lower frequencies. But then there came a point where everything changed. It was one of the most important events in the entire history of the universe, and it was predicted by none other than Alpher and Gamow. We call it recombination, and it also opened the doors to the first light that shone in the early universe. But what exactly recombined? And what does this first light have to do with the first atom? And here ends the first part of our adventure through the cosmos and the world of atoms. If you're curious to know how Gamow and his colleagues unraveled the mysteries of the early universe and what that means for our understanding of modern physics, don't miss the second part. Until then, leave your comments and questions below, and don't forget to subscribe to the channel to not miss the continuation. See you soon!